Hi, everyone. My name is Stefano Della Torre. I have a pleasure here to introduce you our first panel of the afternoon. I'm here with Xiangru directly from Hong Kong. So it's really exciting for us having her here to introducing us what is the parallel EVM. So what is happening beyond the scalability and the velocity in the EVM ecosystem. So thank you very much, Xiangru, and you have your space here. Thank you.
Thank you. I'm going to take the stage. Hey, everyone. I'm super excited to be here. I'm Xiangru. I'm Dido, actually, from the Preda dev team. And I've traveled a long way to make it happen here in Napoli, and I love the city. It's a lovely place to be. And my teammate, just a few days ago, my teammate just gave a keynote speech during EVCC in Ghana, in France, and on Crystality. And now it's my turn to introduce Crystality to you. I will be honest that it will be a little bit tech-focused, but I assure you, like by the second half of this talk, it's going to be fun and cool for the traders and for the builders in this space. So first, let's start with what is crystality. Crystality is actually a combination of crystal and solidity, which means we bring structure, we add structure to solidity. And it would be the first time for solidity developers to express parallelism at the language level. So this is actually a paper just released, published at PPOPP 25, which is kind of a top-tier academic conference in Europe. And I guess that's why we were accepted by EVCC to be a keynote speaker, and just have our debut on the stage. And a little bit quick background of our team. We are a team. I'm not flex here, but our team is really from high-performance system design background. And they are from Microsoft Research, from AMD, and people from Ohio State University. So we've been in this industry for over 5 years. And still, I'm going to share with you what we have been working on today. So firstly, the keyword of today is definitely parallelization. And when we talk about parallelization, it reminds you of a bunch of different things: parallel I/O, parallel ZK snarf, regeneration. But today, we will keep the scope really narrow. We will only talk about the parallelization of transaction execution on Ethereum. So that's our focus today. And for the first time, Crystality brings deterministic parallelization to Ethereum. To make it easier to understand, Crystality sits in the same class as sea level of Solana, and the same class as block STM to Aptos. So when we categorize the layer 1 blockchains in different categories, usually I'm gonna introduce 3 types. So there are no parallelization, OP parallelization, and pessimistic ones. So firstly, we know Ethereum and Bitcoin has no parallelization at all. They execute transactions one by one or sequentially. And for the OPs, like what's adopted by Aptos, Monad, and Say, they are the optimistic one. I'll dive in later for your understanding. And the third one is pessimistic, which is implemented by Solana, Sui, and the latest one, an EIP 7928. It's what we consider one of the most important EIP released by Ethereum Foundation, which basically enforces a block level access list at the block level. So that's basically the first time that Ethereum is taking a huge step towards parallelism on Ethereum. And that's another day, I remember our team say, our day has come. It's time for our show. And so you may ask, so what is Crystality? What's the positioning of Crystality among all these parallelization approaches? So before diving into the details, I'll there's one very key point to understand, which is at the heart of parallelization, there's a very important issue, which is state conflict. So how we analyze and detect state conflicts and how we resolve them and then getting the results just correct. And different answers actually lead to different parallelization approaches. So as mentioned before, Ethereum has no parallelization. For most execution clients, they have no. So they don't worry about state conflicts. We just execute everything one by one. And then for OP, like Aptos, Monad, and Besu is one Ethereum execution client says, we know that they're already adopting OP parallelization. They just ignore, they just assume there are no state conflicts, and they are execute the transactions anyway, and they are going to check if the results are correct afterwards. Then what we do by what is implemented by Solana and Sui is they are going to check and analyze dependency, analyze the state conflicts beforehand, and they will have to know if there are like resource contention beforehand, and they only execute transactions that with no state conflicts. That's what they do. So Crystality's positioning is here. We are a deterministic parallelization that we decompose one transaction into non-overlapping parts. And then we will maximize the parallelizable parts by minimizing the state conflicts. So if that is just too abstract to understand, I'll make it simple here. So this is an axis we use, and the x-axis meaning time or block height. The y-axis meaning different transactions. So when there are a bunch of transactions coming in, there are no parallelization on Ethereum. And Aptos, which is also their block SCM, that's their execution client. So what they do now is they just, as I mentioned before, that transactions are initially assumed with no state conflicts at all. They're going to just execute them and then find, okay, there's a state conflict here. I'm going to abort it and re-execute it with serially or with a different scheduling. That's what they do. So it is especially efficient in low to moderate conflict scenarios, because when there are many transactions coming in, they're gonna execute them anyway and just handle the conflicts when they arise. So when there's no conflict, then they don't need to have to deal with that. But the question is, this is the mechanism that they borrow from database and big data system, where write requests are rare. But in the real blockchain world, we know that because those frequent on-chain execution, there will be inducing spiking gas fees, which might become a performance bottleneck of the system. So next we have Sui, the Sui move today. What they do is they're gonna pre-check the state conflicts. So basically, they will have like a traffic manager, a traffic policer here, just categorizing objects with those transactions are touching owned or those transactions are touching shared objects. And in most cases in Sui, only the transactions touching shared owned objects will be parallelizable. This is what is Sui doing. And it's especially efficient in high conflict scenario. So we know they will just only execute transactions with no state conflicts. But we know in the real blockchain world today, actually most of the transactions are very simple. They just involve very simple operations like ERC token transfer, move token transfer, move NFT transfer. They're just simply deducting assets from one address and adding it to another. So this checking time would be too long. So the whole pattern would be too long checking time and too short execution time. And in that case, the checking time would become the bottleneck of the system performance. And here in this illustration, if you can notice, we make small changes to the y-axis because we need more physical hardware. And this P number 0 to P number 3 actually represent parallel EVM instances. So we're gonna need more parallel EVM instances for executing the transactions. So as shown in this chart, we basically decompose one transaction into multiple parts, non-overlapping multiple parts. The first one is a micro transaction, and the second one is what we call a relay transaction in Crystality. So basically, this means one transaction number 0 is going to touch state A and state X. Then we're gonna just partition this transaction based on their state dependencies. And we see in this, there's a very special one, P number 3, which means on this EVM instance, it is exclusively responsible for dealing anything touching state X. So what's going to happen is if we zoom in on this P number 3, we're going to see whatever microtransactions, relay transactions are going to touch state X will be relayed here, will be sent to this EVM instance and executed here. And this pattern also replicates to all other microtransactions. They will be sent to that specific EVM instance where that specific state stores. And this relaying and the whole executing the mechanism is what we call a deterministic parallelization. So each transaction is partitioned and assigned to a specific EVM instance. That's basically the core idea of this whole design. So this is actually a code example. On the left side, we have the Solidity code, and on the right side, we have the Crystality code. And if you don't read code, I'll just make it simplified for you to understand that if we say Alice is sending 10 USDT to Bob, so what is going to happen in the code is 10 USDT is first deducted, that minus signal over there. It's going to deduct it from Alice balance. And then as the execution flow continues, the system finds, oh, there's a Bob balance here. So Bob balance is stored on another EVM instance. So I'm going to move the execution flow to where Bob's address is stored. And then the logic just continues, the whole flow just continues in that way. So what's different between Solidity code and Crystality code, you see, we've highlighted the differences in red. You see, so for the Crystality developers, they need to highlight, they need to guide guide the system that what kind of data partitioning I'm working on. And the secondly is there is a very important semantic here. It's not shown here anyway. It's relay. So the developers also has to let the system know where the execution flow, how it's going to switch between the different EVM instances. Okay, if that's too technical, I'm going to concluding everything in one table. That's key takeaway here is Crystality, we have a finer granularity of parallelization. That's basically, we're the only one in this space doing that, decomposing one transaction into non-overlapping parts. And that's what we call inter-transaction level. And for the other thing, just like I mentioned before, the OP parallelization execute first, check later, and the pessimistic ones like Sui and Solana will manage check first and execute next. And then for the resource utilization, we will say Crystality, the determinist parallelization one, is excellent. It's the best one. I'm gonna have the numbers, let the numbers do the talking later. I'm gonna show you a performance comparison later. So this is basically, if you zoom out and take a look at the bigger picture, we see, so the states of a contract are partitioned onto different EVM instances. So basically, there are two things worth noting here, which is unlike smart languages like Solidity or moves, Crystality adopts a shared nothing architecture. What that means? It means each single EVM instance has its own disk, has its own memory, has its own computing resources. It's not shared by anyone. So they all operate independently. And that is actually what we borrow from distributed system design from the computer science, just to make things more scalable and more isolated. And the second thing is, beyond a runtime, Crystality is also a code and language, just like Solidity is. So it basically is the first time for the developers to express parallelism at the language level. If there are any coders here, you probably could resonate with me. Okay, so now we come to this image. This image just illustrates how functional relay works, just as I mentioned before. So if Actis is sending 10 USDT to Bob, the system will find, okay, Bob's address is stored on another instance, EVM instance. So the execution flow is going to be relayed to another EVM instance. So it's the execution flow switching between the EVMs rather than the states. Now it's the time to have the numbers do the talking. So we have the performance comparison between Crystality and Solidity, between Crystality and Sui and Aptos. So in the first image, we basically have run this performance test using 3 very typical smart contracts. So the result turns out to be excellent. Crystality delivers up to 99 times over Solidity when there are 128 parallel units, which are the EVM instances where they are executed on. And for the second and third images, basically, we replay the real ERC20 transactions on Crystality, on Sui, and on Aptos. So we see, actually, the scalability here is even more outstanding. All right, enough of the tech talk. Okay, so if you're working on some scaling solutions, or you are a DeFi builder, or you're a trader, and you might be excited for what I'm gonna introduce as follows. And then this is actually a quote, a line I come across on one of the most recent research proposal by Paradigm, which is the top VC in the crypto space. And this line writes, "The future holds 1 million coins within the pool, and today's infrastructure is just not ready." So that actually reminds me that, as with the stable coins currently, as a trendy topic, the stable coins coming on chain, and the crypto world has seen the real incoming liquidity that has been craving for so long, for so much time. And then finally, the money comes. What are we gonna do with it? So in my thoughts, it all comes down to one line. We will gonna keep the money on chain, and we will gonna make them flow like water. But how? Okay, so now I am introducing 2 ready-to-use tools. One is a parallel AMM prototype, and the other one is for the developers to save their efforts when migrating a Solidity codes to Crystality. So basically, the parallel AMM is actually the first parallel AMM in the space that parallelizing transactions from one single liquidity pool. You've never seen that before. And I'll dive into it later, but I'll give you a preview. It basically achieves up to over 10 times speed up on 16 parallel EVMs over Uniswap. And that is something we make AMM firstly faster or fast enough to be the infrastructure ready for mass adoption. And this is actually how we design this thing, how we design this parallel AMM from one single liquidity pool. So from what we observed in the real world, in the real world of AMM, the first thing is that on Uniswap version 2, the top 10 pools accounted for over 31% of total swaps on Uniswap version 2. And this means that AMM trading like Uniswap is highly concentrated in only the top several pools. So if you do parallelize like different pools, it's not gonna help. You're gonna paralyze transactions from one single pool just to relieve that the hottest pool, the hottest spots in the space. That's the first thing. And the second thing is, all right, we know that AMM like Uniswap, they all are based on that constant product formula. So how can we make that happen? If it has to be like executed sequentially, then if we paralyze transaction from one pool, then what it's gonna do? What is gonna happen on the algorithm? So our second observation is that the price impact of one pool is mainly driven by large transactions. And the numbers are from the historical data from Uniswap version 2. The hottest pools shows that over 97% of transactions cause the price change smaller than 1,000. So that means only the large transaction have the significant price impact. So this is actually an overall pattern of our architecture, how we design this. So basically, all the transactions from one pool are going to be categorized based on their price impact. So there are two types of transactions, large sum ones and the small sum ones. And the large sum ones is going to send to a global liquidity pool, which usually has Leaper liquidity. And all the transactions over there are going to be executed sequentially. And the rest, over 70% of small transactions are going to be executed in parallel and in these smaller parallel pods. So what we do and how we make this happen is we treat the liquidity of each pool as a unified one. And we will have two mechanisms, which are periodic synchronization and on-demand rebalancing between the smaller parallel pods and the global pods, just to make sure the pricing is still accurate and still fair. That's basically the design philosophy of our parallel AMM. And we're not only shipping the codes, we were not only shipping the concept, we also shipping the code. So we replay the transactions from the top 3 Uniswap V2 pools, which are ETH, USDT, USDC ETH, and DAI ETH. So what we have found is that Crystality parallel AMM running on 16 cores delivers speedups of over 10 times over a single core execution. And that's enough for the parallel AMM. If you are interested, I'm gonna share you with the link, and so you can try it out yourself. And then we come to this Solidity developer part. We do have a developer tool for all the Solidity developers. So what we do is we input language specifications and we input the 6 contract examples to ChatGPT. We have them learn for a very long time. And then we have ChatGPT successfully shipped 22 contracts from Solidity to Crystality. So that basically there's no bugs. It's just flawless, perfect codes that ChatGPT is able to write. And then we have our Crystality developers have some guidance and prompts and feeding the ChatGPT. Then it is able to ship 10 more contracts. So that's basically covering 77 cases and 45 contracts from Solidity to Crystality. Okay, our ultimate goal would be we will have everything, whatever you write in Solidity, we're gonna ship it and migrate it into Crystality in an automatic way. And that's our ultimate goal. So where we are right now is for the simple codes like ERC20 transfer. So it's a transfer from code. This auto transpiler is doing very well. No bug, flawless codes, and running very well. And what it still struggles is for a little bit complex cases like ERC 721. So the auto transpiler still struggles to retrieve the balance of function output in ERC 721 contract. So that's what we are now. That's the progress we've made till now. And so to conclude this talk, I'm here like laying out a layered architecture. So we have two things actually. We have PRIDA programming model. That's why I said earlier, and I'm from the PRIDA dev team. That is basically the team we founded 5 years ago. And then we have Crystality on top. So on the foundational layer, we have PRIDA programming model. That is the foundation for general purpose parallel contracts. It is decoupled from blockchain architecture. And basically, we can make it compatible with any blockchain, not only Ethereum, and probably Aptos, Solana, and Sui, anyone you name it. And on top of that, we have a Crystality EVM version. That's basically the EVM execution runtime version of PRIDA that we have. And on the top of that, we have a Crystality language, which is a Solidity compatible language that for the first time bringing Solidity to the PRIDA world, to the parallelization world. So that is basically the model, the runtime, the EVM runtime, and the Solidity compatible language we have. And that's the talk for today. And if you're happy to like if you're interested in any part of that, I'm happy to talk to any one of you. And probably I'm actually here to collaborate and to hear thoughts from the scaling solution builders or the DeFi users and builders. Thank you.